So I got this session before lunch, which means we get people hungry enough that we may get some passive-aggressive going on here.
It also means nobody has to walk off to another session.
That's right.
Keep going forever.
Exactly. I get to starve you to death. All right. So my name's Karim Yaghmour, and I'm happy to see that there's a lot more people this beginning of afternoon. So this is the second part of the Embedded Android workshop. So for those of you who were here on Monday, this kind of fits right in. If you weren't here on Monday, this actually still is useful because essentially it's somewhat independent, because I'm actually talking about building the AOSP, making modifications to it, and so on and so forth. For those of you who weren't here, just kind of rapid intro here. So I wrote the Embedded Linux book for Riley, finishing up the Embedded Android one. We should be going to print in about 24 to 48 hours. All right, so anyway, if you don't know more about me, then just Google me out. You'll find more information. All right, so what do I want to do here? Because we only have about 60 minutes before people start walking out because they want to get some food in their stomach. What I want to do is actually talk to you about the Android open source project. How do you get it? How do you build it? What can you make modifications? What modifications can you do to it? I'm very easygoing about these presentations, and in fact, in this one especially, I'd love to have the Linaro folks who are doing Android work pitch in, because you guys are actually doing a lot of this stuff, and therefore you have a lot of knowledge that other people here can benefit from. All right? So just kind of like to do the same thing I did on Monday. Can you just give me a hands up here on who's done any sort of embedded Linux work before? All right. Android platform development? Android app development? A few. All right, good. This is a sane ratio for this crowd. Okay, what and where is the Android open source project? All right, so Google uses Git for maintaining the AOSP. So hereinafter, the Android open source project shall be known as AOSP. So the AOSP is, yes, maintained in Git, but you don't actually use Git directly to fetch it and manage it. What you do is you use a tool called repo. Repo is layered on top of Git. And the rationale for that seems to be that when you actually do Git manipulations, it has to load it all into RAM and do these things in RAM and whatever. So given that the code base is huge, it kind of becomes unwieldy. All right? So they have this tool which fetches what's called a repo manifest file, which has absolutely no relationship whatsoever of what you may or may not know about manifest files for applications. Instead, this manifest file is an XML file that has a list of all the Git repositories repo has to go fetch. So this is about 150 to 200 Git repositories that have to be fetched by repo. And essentially what you do is you first get repo, make sure it's somewhere in your path, and then you do repo in it, you give it a manifest file, and then you do repo sync, and off you go. You know, this, depending on the speed of the, the connection you have with the internet, it will go and fetch the official repository from Google. Now, if you don't give it a branch, like -b, which I'm doing here, it'll get the tip. The tip doesn't always build, so, just get yourself a branch, all right? Or even better, in this specific case, get yourself a Linaro manifest, right? And off you go, because you guys have been doing very good work at actually providing optimized trees for the boards that you guys are supporting. And oftentimes, actually, I direct people to actually get the Linaro branch or the SOC vendors' branch instead of going straight to Google's. Yes, sir.
And our tip always builds.
Your tape always builds. All right. May I quote you on that? All right. So essentially, the AOSP that Google maintains is good for the lead devices they have, but the specific board you have, it may not be so useful to you. Okay? So this is how you get it on your machine, and voila, you get yourself, gigabytes of sources. What do you do with that? All right, so what's inside the AOSP? So we can look at a boring slide, or I can walk you through the stuff on my computer. All right, so the mic's kind of is going to go dead unless I actually kind of find myself a montage here to show you stuff. maybe I can actually get the laptop a little bit closer here. All right, since we are not, all righty, just gonna lower this mic a little bit, or I'm not doing it right. The other way around. Yeah, well, I can't type and hold the mic, so. Alrighty, so let me show you around my AOSP sources. Here's a tree I have, which is essentially 237. Okay, you can't see anything, right? So let me actually put that in a class-friendly form factor, and let me actually do some other thing here. Let me remove my standard Emacs configuration and change it. So this is going to be whatever. Presentation. Alrighty. Okay. If you're using VI, I'm sorry for you guys, but anyway, I'm an Emacs person. So what is in here? Okay, you have a whole bunch of directories, and the question is going to be, what's in each one of those? Okay, so if you remember a little bit the architecture diagram that I showed you on Monday, or if you don't, you can just go on SlideShare. The slides are up. You can just go get it and look at it. I'm going to refer to essentially some of the components we described in there. Okay, so this is a 237 tree. So this is Gingerbread. The Jelly Bean one has a little bit more directories. I actually find this one to be a little bit more easy to explain because the stuff that's inside of it is a little bit more obvious. So you have the Bionic directory, which is all the libraries which are part of the C library, like libc, libm, and so on. You have Bootable, which has some bootable boot-related stuff, including the ODA, over-the-air update stuff. You have Build, which is the build system. Okay, the build system is non-recursive. And I will show you what that means in a couple of slides. But just remember that if you're used to configure, make, install, this has nothing to do with it. Okay, CTS is the compatibility test suite. Even if you're not actually doing a handset or a tablet, you may find this useful for quality assurance purposes. All right, it will show you whether your stack is behaving properly or not. Dalvik, that's the Dalvik virtual machine, which interprets Java bytecode. Development is part of the development tools. Device is a very interesting directory because this is where OEMs and device manufacturers are supposed to add support for their devices. Okay? They're not supposed to kind of like change the rest of the tree. They're supposed to add a directory in here. And just to give you an idea here, the way it works is a device at the kind of like the first level has a directory per manufacturer or vendor. And then when you go inside the vendor's directory, you should find yourself a directory per product. Okay? And inside that directory, you will find the support stuff that's specific for that board. Make sense? And the goal of that is that if you've got this layout of things, if you move to a new version of the AOSP, you should be able to just copy that directory into the new AOSP and then fix your code to use the new APIs, and you should be all set. That's the purpose of having this kind of modular way of doing things. All right, external is all the external projects they are importing into the AOSP. So this includes stuff like zlib, WebKit, SSL, you name it. A dbus. Most of these you should be able to recognize. Some of them were not known in the open source world prior to being included in the AOSP, but most of them were. Then you got framework, and especially, at least in the branches up to 2.3 frameworks base. This is where all the framework stuff of Android is. So the system services, the API that app developers are used to using, that's all in here. You've got hardware. This is where the hardware abstraction layer is implemented. And remember I said that the way hardware is supported in Android is by providing HAL modules. And so long as the module for a given piece of hardware exists, then Android knows how to talk to this hardware. You'll find that the contract there, or the definition of the interface inside lib hardware, include hardware. You'll find these header files that describe to you each of the contracts in regards to each piece of hardware. Okay? Okay. libcore is the JDK replacement. NDK is for the native development kit. The out directory that you see on my tree over here will not exist when you get yourself an AOSP. This exists here because I built this tree. All right? And if you wipe this directory away, it's the same thing as if you do make clean. Anything that gets built inside the AOSP goes in there. Nothing is placed anywhere else. So whereas in the Linux kernel, for example, you'll find .o files right beside .c files, you won't find any of that in Android. It's all in this out directory. Yes, sir?
One minor point, if you're using a Linaro tree, is that's not completely true. So we haven't completely...
Darn!
So just watch that.
You're breaking it, aren't you?
Yeah, the reason for that is that we are including some external projects that still use their own build system, and for those it's typically hard to move the output to the out directory.
Right. So essentially, if you're including inside the AOSP things that come from external projects, and you're asking the build system of Android to use the original build system of the project you imported, then whatever that original project did will continue happening. So for example, if you get yourself the TI Android dev kit that provides support, for, say, for the BeagleBone, you'll find a kernel directory in the AOSP. And that kernel directory is where the kernel for that board is, and it gets built in the kernel directory as it usually would, not in the out directory. Okay. Then you got packages. So these are the stock packages which are part of the AOSP. And if, for example, you've got packages apps. This is where all the stock apps that you would see on a phone are typically located. So the browser, the launcher, the calculator, email application, they're all in here. Okay, pre-built is a whole bunch of native, binaries which are compiled kind of from factory for you to use, like the actual tool chain which is used to build the AOSP, and some kernel images and stuff like that. I think if my memory serves me right, you guys are actually building your own tool chain to build the AOSP. Is that right?
Right.
You are. Okay. Then you got SDK, which is essentially what generates the SDK that app developers use. And finally, you got system, and especially system core. This forms the basis of the embedded Linux system on which Android is being built. In fact, that's not my kind of wording. That's their own wording. If you open the README file, it's there. Okay? So you'll find the ADB tool in here. You'll find Toolbox. You'll find the shell, and so on and so forth. Okay? So that's kind of like if you browse the sources on a directory by directory basis. If you want to look at it in a kind of, quote unquote smarter way, you can look at the architecture diagram that I was showing on Monday, and essentially what you got here is this kind of layout. So the kernel itself at the most bottom part is not part of the AOSP, at least not the standard AOSP that Google puts out. Then you got the libraries. They are spread around, so there's part of it in Bionic, part of it in external, part of it in frameworks. The HAL is mostly in hardware, at least the definitions. The actual implementation will be device-specific. So something like device, Samsung, Crespo. All right? The native daemons, there's a bunch of them all over the place. Init and Toolbox, they're in system core. And then the system services are in framework space services. Some of it's in media. At least that diagram actually shows it to you for Gingerbread. In the case of Jelly Bean, some of this stuff has moved around. So for example, some of the native services are now in frameworks native services instead of being frameworks-based services. Okay? And if you're looking for the API that app developers kind of see, you can find that in frameworks-based core. All right? If you go in there and you're an app developer, you should immediately recognize everything that you see, because that's what app developers use. Okay? Any questions about the content of the AOSP, or how does it all match together? We're good so far? Yes, sir.
How does Linaro tree and the
What's the difference between the Linaro tree and the main tree? I guess that's a question best answered by you guys.
Sure. Pretty good idea, right?
Yeah. So obviously the first difference is that we support different hardware. So there's a couple more things in device. So we have device Linaro Common and device Linaro Panda, device Linaro Origin whatsoever. Then we have a number of changes that make stuff work with newer compilers. Original AOSP is supposed to be compiled with GCC 4.6. We are typically building with 4.7, and the version of that comes out of our toolchain working group, which is actually closer to 4.8 in some parts. And we are already working on making it work with GCC 4.8 and also with Clang 3.3. Then there's some generic optimizations in there. For example, we have rewritten all the string handling routines in Bionic to be faster on Cortex A9 CPUs. There's some modifications that just improve support for certain hardware we are supporting, like changing IOCTLs that are being used in the frame buffer driver. And then there's just more or less random collections of fixes for stuff we've come across. I think that's pretty much the most important parts.
You also, if you grab a Linaro tree, grab the Linaro tree, you're also going to find that you have bootloader and kernel sources.
Right.
Okay, yeah.
Big departure from.
Yep, bootloader and kernel sources in the AOSP, yep. All right, good.
There's support for U-boot, while AOSP only supports fast boot.
Okay. All right, so that's for the kind of like the tie-in with the the architecture diagram which I showed on Monday. All right. Unfortunately, the video of that is also available on the net, courtesy of Sharbox here. So if you want to go back and see the full thing, you can actually go ahead and do that. Now, if you want to build the AOSP, you need yourself an Ubuntu 64-bit machine running 10.04. It's not me saying it; that's them saying it. Because that's what they have on their build farms.
Any other Linux distribution will generally work.
Absolutely, which is exactly what I was about to say. So, which doesn't mean that you can't use something else. All right, you can, in fact. So this is 12.04 and it works just fine. All right, and you can use something like Fedora or whatever. It just happens that that's the setup they have kind of certified, so to speak. Now you're going to need in a bunch of different packages. This is just an example. Don't assume that this slide is authoritative. It is not. But if you go to source.android.com, they will actually show you the packages you need for your version of Ubuntu. Okay? Now, once you have those things around, what you do is you type something like /build env setup.sh and then lunch. Let me actually show you what that does. Okay, so here's build env setup.sh, and here's lunch. Lunch gives you a menu. Yes, we are about to go to eat, but this is their lunch menu. Then you type enter, and then it presents to you essentially the configuration summary of what you have. Once you've done that, you can actually type make, and it will go out and actually build the AOSP for you. All right? And so depending on the power of your machine, this will take any sort of random amount of time. I'm a hockey person because I'm Canadian, so therefore I go watch hockey games. Insert whatever sport you've got. Go watch a game while you're building and come back. Canadians in here? Yeah? All right. Wow. Okay, cool. Once it's done building, you can actually start it up. So what I've done here is I've actually built it right before I came in here. So type emulator and enter. All right. And here comes the emulator for you to actually kind of play around with Android as it's booting. And this is the same emulator that app developers use. Of course, I'm building it here for the emulator. You might actually be building it for a real device. And at the end of this build process, you may be doing, fast boot, flash all, whatever it is that you're going to be doing to actually flash the thing on a real device. You might be programming an SD card, whatever it is that's relevant to the work that you're actually doing. All right. Now, remember that whenever you actually open a new shell, you need to rerun the cnv setup.sh and lunch thing if you want some of the environment variables to be re-enabled and some of the commands to be available to you. Okay? Note that there is a space. It's dot space build env setup.sh. For those of you who aren't familiar with this kind of semantics, the thing is if you run a shell script, your current shell will spawn a new shell to run your script. All right? And when that script is done, it goes out and it comes back to the original shell, and then whatever environment variables were set in the child shell are gone. So by doing dot space, you're actually forcing it to run it in the current shell. Okay, a few build tricks. So the AOSP is fairly large. Let me give you an example here. So if you look for the sources of, say, the thing that displays the status bar. So let me clear this again. So I would go into framework space, packages, system UI, src, and system UI status bar. Now, if you remember the path I'm in over here, we're about 9 to 10 levels underneath the top level. This is very far. Okay? If you want to go back to the top, you typically have to do cd ... It really becomes very painful very fast. Or, if you've got build env setup.sh and lunch having run, you can type croot, and you're back at the top. Okay? And the cool thing is that there's kind of another command that allows you to go straight into the tree, whatever you want in the tree. So, for example, let me pick a file here, ticker.java. All right? So, let me tell the system that I want to go to the directory that contains that file straight away. So I can go dir ticker.java. Okay? It says creating index. All right? As soon as it's done, it takes me back to where I was. This is very powerful. All right? So let's say I want to go to the system server's sources. I could go dir system server.java. Here we go. We're in another directory right now. Okay? And of course, if you've ever done this sort of stuff, you're like, okay, what happens if there's multiple ones, right? So let me show you. Go dir init.rc. Which one you want, right? You can select which one you want. Okay, so this is very, very, very useful. You've also got MM and M. If you've ever built the AOSP, you know that it takes quite some time to kind of start up, and then actually quite some time to run. Sometimes you just want to build one thing and kind of test your changes locally. That's what MM does. You just cd into the directory that you were making changes to, you type MM, and it builds just that thing. All right? M will allow you to build the entire tree regardless of where you are. So you just type M, and it will go back to the root and run the make. Yes, sir? Yep.
You can also just $sign alt PWP.
Okay.
And you go to previous PWP.
Sure. Yeah. Right. Or cd, hyphen, or or you can play around with push d, pop d, that kind of stuff. All right. Now, speeding up the build. The build of the AOSP is very intensive. All right. So on this laptop here, it will take me about 80 minutes to build Jelly Bean, 30 to build Gingerbread, and your results may vary. So some of the tricks that are useful to speeding up the build, of course, a very powerful system in terms of CPU, but it's a very I/O intensive build. All right, so if you can get the entire tree into the file system cache and RAM, then that's the fastest thing you can find. All right. The second thing to that is SSDs. All right, solid state storage. And the other thing you can do is use Ccache. Who's familiar with Ccache? Okay, not everybody. All right, so Ccache stands for compiler cache. So the thing is in C, before you actually compile the C file, it goes through the preprocessor, and then it actually compiles it. And somebody kind of thought about this neat trick where essentially they take the result of the preprocessor, and then they do a checksum, a hash of that, and then they take the resulting .o. And at the next build, if they find at the output of the preprocessor that they already have a .o that matches the same hash, they just use the .o instead of running the compiler. And that will actually speed things up. There are some cases where Ccache will bite you, but in most cases it does a brilliant job. So the first time you don't get any speed ups, but the next time you do. Okay? Do you guys want to add something on the build side of things? Or?
I was curious,
Yep.
when can Ccache bite you?
When can Ccache bite you? So here's a case that I've encountered. So essentially, I created a tree on my machine. I pushed it over to GitHub, all right? And I had been building this tree using Ccache for a while. So the cache was warm and it built fine. Then I created a new directory and fetched that same AOSP. And I did a diff of both of them. They were identical. I mean, diff returned no difference. But the build of the second one just wouldn't work. So in that case, it bit me. I don't know. I still don't understand why, but just kind of like a caveat out there. Okay, what's the architecture? Yes, sir.
Another way to speed up the build a little. Usually, when you just say make, it will run the droid target.
Yep.
But you can save some time by just running make droid core instead. That will avoid generating Javadoc documentation and stuff like that. But if all you're trying to do is seeing whether or not something boots or whether or not you just fixed a certain bug, you don't need all that stuff.
Right. Right. And of course, there's one thing that's assumed here is that you're using the -j parameter of make to actually run multiple build threads in parallel, not just not just make, because that's really slow. Okay. So the build systems architecture is kind of fancy. Okay. Think of it this way: they have created a non-recursive build system which is based on somewhat object-oriented inheritance, all right? So the way it works is that there are not make files, capital M, in every directory. Instead, what you have is parts of the sources are identified as separate build modules. Nothing with kernel modules involved here. Every one of those modules has a corresponding Android.mk capital A, okay? And what the build system will do when it starts up is it will run a Python script looking for all those Android MKs. And then it will kind of almost group them all together in a single makefile. And then it will actually process that single makefile. Okay? And the location of your Android MK doesn't really matter. What's important is what's inside that MK. All right? And I'll show you a little bit later how to add support for your own board, so it will give you a very good idea of what's going on here. But let me actually show you what those MKs look like, so you understand kind of like the mindset they're using here. So I'm going to go fetch two Android MKs, one for a command line utility, and the other one for an actual application, an app that actually shows up on your. All right, let's go for, say, something like frameworks-based commands, service. So if you're familiar with the service command line tool, you know what this is. If you're not, I invite you to actually look that up. Very useful tool. And let me go get packages, apps, say camera, and open the MK for this one. All right? Now, okay. What we have on the left-hand side is the recipe for building the camera app. And what we have on the right-hand side is the recipe for building a command line tool called service. Just visually looking at this, you can see that there are a lot of things which are similar. All right, it always starts by this, local path equals and include clear vars, and then ends with something like include build _ foo. Okay, remember I said all those MKs are kind of put right on top of each other. So assume that those two snippets, when it actually gets built, are sitting straight one on top of each other. All right, they're not in separate files. All right. And the other thing is that they're using those local _ variables to explain to the build system how this specific module gets built. And the local _ variables, okay, they are identical or almost identical regardless of the type of package you're building. So you can see here that there's the one on the right-hand side, it's actually compiling C files, and it says local src files equals service.cpp. On the other side, it says local src files equals call all Java files under. This is actually a function, a makefile function that will go and look for all Java files underneath the current directory. So in both cases, we're using local _ src files, regardless of the fact that we're using different programming languages, and we're generating different things. So what happens is if we did not clear variables at the beginning of each of these snippets, the previous or subsequent, the previous snippets would pollute us with the local _ variables. all right? Or, we would pollute subsequent Android MKs with our local underscores. So that's why you have this clear vars thing, all right? And the key operator here is the build, as the include build underscore at the end here. So on the right-hand side, it says build executable, because we're building an actual binary for the command line. On the left-hand side, it says build package. That's because we're building an APK. So you have build library, build Java library, build static library, build whatever. There's like 20 of them out there to explain to you how to tell the system how to build different things. Does that make sense? So that's how the build system kind of works. The location of the actual module, which is described in this MK, doesn't matter. It's the recipe in this MK that matters. All right. So what do we get as an output once this thing builds? So let's go looking again in my sources here. So clear. Target, product, generic. OK, so here's the output directory. So all these IMGs, all these image files, this is what gets burned on the actual device or in the flash or gets run by the emulator. OK? You got 3 of them. You got RAM disk, you got system image, and user data. RAM disk is generated using this root directory. System is from the system directory, and user data comes from this data directory. The RAM disk is mounted and is packaged with the kernel, and then mounted by it at boot time. And you mount the system image and the data image onto that one once it's started. So the RAM disk image is kind of like a very tiny bootloader-like root file system. Okay? So that's for the output that you get. Now, the interesting thing, of course, is once you've built this and you start running it, what do you do next? If I want to interface with this, how do I do that? And the tool to do that is called ADB. So I already have an emulator running in the background here, as we saw. And I can do something like ADB shell. And I'm shelled into the device at this point. If I do something like, oh, come on. It's not offline. So that's one thing about ADB. It's kind of flaky sometimes. So cat proc CPU info. We are, from the perspective of the emulator, running an ARM processor. All right? So there's a lot of things in the Android stack which are replacements for existing Linux things. ADB is a novelty that's part of Android. And really, it's very useful. So you can use it to shell. You can use it to copy files. You can use it to forward ports. You name it. Everything that you do during platform development will somehow involve ADB. So far, so good? Yeah? How are we doing on time? 20 minutes. All right. The AOSP that you get not only allows you to generate the actual images that will run on the target, it also allows you to generate the tools that app developers are using. Okay? So you can build your own SDK, your own NDK if you want to, and distribute those out, so to speak. Why would you want to do that? Well, because the official SDK and NDK that are being put out by Google are for their current devices and what they're doing right now in the market. If you're creating an embedded system, and in 10 years' time you need to service that unit or create an SDK or make changes, you better be able to generate your own SDK, okay, from the sources that you used. Hence, the need to understand how that works. So this is actually relatively simple. You do build env setup.sh, launch SDK, make SDK, of course, make SDK -j, whatever, and that will build you an SDK. Now, if you make changes to the fundamental APIs, which are published by Google, all right, at some point during some of the build operations, it will complain. And it will say, wait a second, you've just changed the API, all right? You need to talk to Google to do this, right? Or otherwise, please type this. And what they ask you to type is this make update API. And essentially, the stuff that's underneath this, so let me actually show it to you source-wise. If you go in the sources, so let me go actually show you on my side here. So if I go to frameworks, and then base, and then API, you see a whole bunch of XML files here. So this is Gingerbread. Let me actually show it to you on Jelly Bean. Same thing. Just give me 1 second. So again, so frameworks, base, API. Let me actually bring the other one in focus here. So you can see that in Gingerbread, I have XML files 1 through 10, and in Jelly Bean, I've got XML files 1 through 13, and then I start using text files. I'll talk to you about that in a second. But anyway, these are the API levels. So each new version of Android changes the API, and they essentially have an XML file describing that API. So when you change the API, they test what you have versus what's being published, and they say, wait a second, you've just broken it. Okay? And when you do this make update API, it generates this current.xml file, or in Jelly Bean, the current.txt file. All right? So why'd they change formats? So they were using XML, and at some point somebody said, let's just switch to JSON. And that's what the text files are. All right? Okay, now once you've generated your SDK, like any other SDK, you would tell Eclipse where to find it. You do Eclipse window preferences, Android, SDK location, you give it the location. But that, in and of itself, is insufficient. And I have no idea why you have to do that second step, but if you don't, I guarantee you that SDK doesn't work in Eclipse. So you have to actually go in the SDK manager. That's the actual tool inside Eclipse that allows you to go and fetch platform support for various versions of the API. And you have to force it to update something. Okay? If you don't have it update something, then the next time you do a new project, it will create a project, but it will create a broken Android project. Yes, sir?
So this is actually pretty cool. Personally, I never knew you could do this out of the AOSP tree, so I appreciate you looking and figuring this out. One question though I have is, now that they've, in later tools, they've integrated Eclipse and the Android toolchain, or the Android tools, into one single distribution.
Sure.
So have you done a make SDK on a 4.2.2 tree, and does it actually work out of the box now from the AOSP tree? Okay,
does it work out of the box in the current versions of the AOSP? I haven't tried it with 4.2, but this has been working for almost forever, because I'm suspecting that's how they're generating it themselves. So I don't see any reason why it wouldn't work. With regards to the packaging, the fact that they're right now kind of putting the image of Eclipse with everything included inside of it, not sure that that precludes in any way, shape, or form building your own SDK. But I haven't looked at that, all right? But until, say, a couple of months back when they weren't yet doing that, it worked still for very recent versions of the plugin they had. Okay?
Cool.
So if you want to generate the NDK, all right, the build system is slightly different. They don't use the AOSP's regular build system. They have their own build scripts, which look very much like traditional cross-tool chain generation scripts. Okay, they're like shell scripts that will go fetch the images, build the whole thing from scratch, and so on and so forth. Okay, and if you type that in, it will give you kind of like a warning. Do you really want to do this? It's going to take a long time, and then you say yes, and it goes out and actually generates an NDK. Sorry. Okay, which brings me to the CTS. So the Compatibility Test Suite is essentially a set of software tests that are part of the AOSP that allow you to test whether your device conforms to the spec that Google puts out, yes or no. All right? If you're not putting out a handset, this may be of little use to you, except for quality assurance purposes. Okay? If you want to check whether parts of your stack are behaving as they should, this will allow you to do just that. So you go in the, this actually comes from them. So you download CTS, it runs on your host, loads tests on the target, returns the results, and builds you an HTML file with pass or fail for the test that it runs. So the way you actually build this, you do build env setup.sh, make CTS, and it will generate in out host Linux x86 bin a CTS binary. The CTS binary actually gives you its own shell, which has a online help. And then you can do something like CTS start, plan CTS, and it will run all the tests for you. And this will run for quite some time. I was actually curious, do you guys have experience with playing around with this a lot?
So one of my big mistakes is the Android lead. Since I'm in a confessional mood.
There you go.
To not focus very much effort on getting CTS to work and using that, we developed our own set of tests, which is always a mistake. But I will say that in the last few months, we have gone hard in this direction to ensure that we are primarily CTS driven, and we are working through all of the issues for all of the targets to make sure that they all run CTS in automation.
Okay.
So it's something. I kind of got beat up a little bit on it, and I thought, oh yeah, gotta do this.
All right.
It's very important.
And the other will be testing, training device for me at least.
That's right. Karim in the back has taken the brunt of this mistake and is responsible for actually running all the CTS tests manually until they are working in automation. So, big thank you to Karim for doing that.
How long it takes?
What's that?
How long does it take?
Yeah, CTS takes what, a day? You think,
Yeah.
to run completely.
Because we are not running through plan, so I ran on.
Hang on. We'll need Mike, yeah.
The plan was not running, so I had to run all the packages individually, so it took me around 21.5 hours to be precise.
Okay.
And sometimes the ADB was not working.
Okay.
So, it took another 5 minutes. I'll say 20 to 30 hours.
Yeah, I've seen it take hours, so depending on.
On one platform, all these, there are like 134, there are like close to 18,000 test cases, CDs, and around 134 test packages, and around 6 or 8 test plans. How long does that take? For me, it took around almost 25 minutes.
Can you repeat?
One minor.
We didn't hear that in front. Can you repeat that?
Yeah, so what Kari said was there's around, 134 individual package tests, plus there's the test plans that you can run through, which actually call into the package tests. And on our platform, which we're doing development on currently, which is actually a simulator, it takes 30 hours.
30 hours, there you go.
If you kind of account for it being a simulator, it's probably on the order of 3 or 4 hours on the real target.
Yeah. A certain number of hours at least.
Yep.
Tyler can answer.
Yep. Tyler? Go ahead.
OM 4470.
Yep.
18,000 test cases, 7 hours. Now, this depends on how many fail.
Okay.
If it fails quickly, it'll run through quicker. So if you start getting CTS results in 3 hours, you've got a big problem.
Thank you, sir.
Just FYI.
Okay. So and essentially, there's a whole bunch of range of tests, and so if you're, again, even if you're not manufacturing a handset or a tablet, this may be relevant to you because it will help you understand whether your stack is behaving normally or not, quote unquote. Okay, which gets me to the interesting part of the conversation. How do you hack your way around the AOSP and add some random stuff? Okay. So the first thing that you'll probably want to do if you're doing any sort of embedded development, such as I am, is to add your own board and go from there. All right? So let me actually show you how to do this. So if I want to add a device, the first thing I need to be doing is essentially creating myself a directory inside the device directory. So let me actually go ahead and do this. So let me close these guys off, go back to my other shell out. Okay, so if I go in device, I've got these manufacturers, okay? I'm going to add my own, all right? My own vendor. So make directory Acme, all right? Go in here. Of course, I don't have anything at this point. So let's create ourselves a product. Let's call it the Coyote Pad, all right? For catching fast birds. So what do I do next? What do I need to actually get this to do anything? All right. If you go back to my architecture diagram for the build system, and I'm going to use this kind of as a lead here, I need to provide a bunch of things to the core of the build system. All right? I need to provide a product description, a board description, along with the rules for building all the modules. Well, those are already in because the modules are already in the AOSP, the stuff that I want to build, like the launcher, the command line tool. So I don't need to provide those. But I need to tell the build system what products I want in the description for the board. What is a product? So this is interesting because think of the AOSP as a very rich Linux distribution in which there's a tremendous amount of packages. You don't necessarily want all of them, all right? And a product description essentially tells the build system, here's the subset of the packages that are in there that I actually want. And the board configuration just tells the build system, here's what actual type of hardware you're going to be running under, all right? So to provide the product description, there's 2 files that you need to provide. One of them is called Android products.mk. And the essential role of that one is to just point to the second file that you have to provide, which actually provides specifics about your board. All right? So let me show you the files I've got for that. So let me actually, given that I've actually done that before, I'm actually just going to copy off files that I already have. I'm going to show you the content. So let me copy off of this Android AOSP 234. Let me copy from device Acme. All right, Android. Yeah, Android products.mk. Copy this guy here. So, what's inside this file? So, Android products.mk is pointing to, in this case, to a certain directory, and what I need to, to local dir full coyote pad. Sorry, the line wrap is incorrect here. Okay. So what I need to provide now is this full coyote pad .mk. Yes, sir? 5 minutes. Thank you, sir. And that should be sufficient. And that's actually cool in and of itself, that it actually doesn't take that much time to actually do this. So if I copy now the full coyote pad over here, I now got myself this full coyote pad that describes essentially the product to the build system. Okay, I need to just tweak this guy a little bit because there's some stuff in here which is irrelevant for us. So let me just remove this hello world because this actually doesn't exist in my specific case. The other thing I had to provide, like I said, is a board configuration. Tell the build system how to actually build this for the specific hardware I'm using. Of course, in this case, I don't really have any hardware, but let's just get one in here for the sake of a conversation. Okay. And what does this guy look like? What's in here? It says, no kernel, CPU, API. Of course, if you look at the Samsung Crespo, it's got a lot more information than this basic snippet here. All right? The last thing I want to provide is an actual file, an actual Android MK that actually tells the build system how to build any of the content that may be inside this specific directory. If I have modules which are specific to this hardware, this MK will make them build. All of this stuff is out and is in my slides, so you'll be able to fetch it afterwards. Okay? So, will this be sufficient? Will I find my device inside the actual list of devices if I type lunch? Apparently not. Okay? It's not in that list of options I could have chosen. Okay, there's one last thing you need to provide. So I have to provide a shell script. So let's go for vendor setup.sh. And vendor setup.sh, all it does is tell the menu system that here there is a new target for building. All right. And now if I go back, as I had done earlier, and I do lunch. Actually, no, sorry. You have to rerun env setup.sh. So now if I do lunch, I actually have my coyote pad in the list. Okay, and if I type make, it will. And if I choose that and I type make, it will generate the stuff for this board. Obviously, that board is not doing anything useful at this point. All right, there's no hardware support. There's nothing at all. But it's your starting point. And it's interesting that I can actually do this in like 5 minutes. Right. So to get going with this is very, very rapid. Now, of course, there's other stuff that you may want to do than just adding, of course, your own device. Here's actually kind of like the checklist and the actual various files. You may also want to add new applications. Okay. Generally speaking, you probably want to put those inside your device Acme Coyote pad. You provide an Android MK for the app, and you add the app's name to product packages in full Coyote pad. Just to show you this, if I go back to that other file I had over here, if I open full Coyote pad, there is a product packages. In here, I can list the stuff that's specific to this board. And then add an app overlay. If you want to change, say for example, the default strings which are displayed in the launcher, instead of changing the launcher, which is in the top level packages apps directory, you can just add an overlay in your board specific directory that overrides the default XML files which are being used by that app. You can add native tools. Here's again kind of like a list of things. So you would usually put that in your device-specific directory, but if you want to add it globally, these are the locations where you'll find essentially most of the native tools and daemons which are part of the AOSP. Same thing for libraries and so on and so forth, the list of stuff you can do with the AOSP. All right? And that's how you roll in 1 hour a description of what you need to do with the AOSP and how it works. Any questions? You're too hungry, eh? All right, folks, have fun, and I'll see you tomorrow and Friday for the last 2 sessions.
Thank you.